All right, so we're going to go ahead and start in on chapter 12 today. And as you guys hopefully from the reading saw, really this is at the heart of phase changes. So it's kind of funny because I feel like we talked about solids, liquids, gases, and how they're different from the beginning of the semester. Not even this semester, I mean from the beginning of the year. So first or second day, I was like, you guys know the differences, right? So now we get to actually talk about why they are that way. So when you have a solid, this sort of is maintaining its shape. In the last class, it looked very much like an ice cube. So when you have a solid, this is supposed to be water, it relatively maintains its shape, right? You might lose some of the molecules, but think of an ice cube sitting on, in the freezer, okay? There still is molecular motion, like the molecules and atoms are still moving around, but they're moving around a lot less slowly than we're gonna see in liquids and gases, okay? They also maintain their structure pretty well. So if you think of why snowflakes look the way they do, that's because they have a particular structure that is ideal for how those molecules are being held together, okay? When you go to a liquid, now things are much more, I was gonna say free-flowing, which is apt for a liquid. They're much more able to move around, okay? With the increase in temperature that comes when you convert something from a solid to a liquid, you're increasing the molecular motion, and therefore things are able to move away from each other more. The molecules themselves are able to move away from each other more. That's why they fill the bottom of a container rather than stay in a rigid shape. But they don't have enough motion yet to actually escape from each other, okay? And we're going to talk about what forces are holding the molecules together, like why do they stay as a group. And when you add enough heat to move them to a gas, so that's this one here, now they've gotten enough energy that they can actually separate from each other, okay? So they're not bound to each other, they're able to move freely in the container and kind of behave independently. They do still bump into each other. There might be some small interactions occasionally, but for all intents and purposes, they're behaving independently. An important thing to notice is the oxygen and the hydrogen are still bound together, right? It's still water. We haven't broken any covalent bonds. We've just separated the individual molecules from each other, okay? So I'll draw a picture on the slide, but it's really important to understand that covalent and ionic bonds are very strong compared to these forces that are holding molecules together, all right? Okay, so let's switch over to that. And let me just kind of reiterate that. We may come back to this in a second. So covalent and ionic bonds are up here. We're going to say this is like a strength scale. And these forces between molecules, they're called intermolecular forces. And I will abbreviate that as IMF pretty much from now on because it's long to write. Those are the ones that are between molecules. And these are the things that must be broken, or in the case of solid to liquid, broken and reformed and broken and reformed in order for a phase change to occur. So I think I have this on a future page, but I'll just put it here as well. So when we go from solid to liquid to gas, this is where we're breaking those intermolecular forces. So if you're adding energy to break the force that's holding liquid molecules together to let it go to a gas, That's why these are the forces you're breaking. You're not going to break those forces up there. That requires a lot more energy than you would be providing just with your stove. Okay? So within intermolecular forces, there's lots of different types. And by the end of today, I should be able to give you a molecule and you'll be able to identify what type it is and its relative strength compared to another similar molecule. Okay? And that's going to tell us a lot about like what its boiling point is. Boiling point is just like an indicator of how much energy would have to be added to something in order to break those intermolecular forces. Let me see if I have a space. Yeah, perfect. Okay, so this is where that simulation is if you want to look at it again. I kind of talked through these questions, but for your notes at least. Okay, so those intermolecular forces are these dotted lines that are being shown between water molecules. Think like interstate highway between states, so intermolecular between molecules. The bonds that are within a molecule, those would be called intramolecular. Intra is within, so within a molecule. We don't typically call them that. We just call them like a covalent bond or an ionic bond. And do be clear, when I say IMF, I'm talking about intermolecular. I'm talking about the forces between molecules. Also, I will try to use the term force when we're talking about these forces between molecules. Unfortunately, we can't get away from the fact that one of them is called a hydrogen bond, but it's not a bond in the sense of like a chemical bond. It's not a covalent or ionic bond. It's just another type of one of these forces. Okay, so if we have to break these intermolecular forces in order to move to a solid or a liquid or a gas, from a solid to a liquid or gas, the energy that's going to be required to do that is going to be related to how strong they are, right? So if this force is weak, it's not, but let's pretend it's weak, then it would take little energy to break it so that it could become a gas. Now, the way we usually see that energy is with temperatures. So when we talk about melting an ice cube, we're just melting it by bringing it into an environment where there's a higher temperature, right? We pull it out of the freezer and bring it to room temperature, okay? So that process does allow heat to go from the surroundings into the system, the ice cube, because they're equilibrating in temperature, right? So Q would be positive. It goes into the system and provides energy for that process to take place. So we could even draw like an energy diagram to show like here's our liquid, and it would have to go up in energy to become a gas. We need energy for that process to occur. And that amount of energy is related to how strong it is. So let's let this be the weak one. And if we had one that was strong, it might look like this. It might take significantly more energy to break that interaction. So what might that mean then about the temperature that we have to bring it into or bring it up to in order to get it to melt? So an example that I thought of off the top of my head. So you take an ice cube and you put it in room temperature and it goes ahead and melts. This is probably not the best example with what we're about to talk to, but I won't tell you why, and then it'll be fine. Whereas if you've ever used coconut oil in like cooking, it's a solid in room temperature, but like the second you touch it, it becomes a liquid. Okay, so its melting point is somewhere right around between room temperature and body temperature, and that's enough energy to get those forces to break. Whereas water, you just have to put it at room temperature and it turns into a liquid. That's a solid to liquid, obviously, transition. So the stronger it is, the higher its melting point is going to be, the higher the temperature at which it would move from a solid to a liquid, or the higher its boiling point would be as well. Yep.
I'm not sure how to phrase this question, but like, does there need to be like at least like one strong and weak bond liquid to gas within a structure, or is it just kind of varied?
It's varied. So it really is going to depend on the structure itself. So water actually has relatively strong interactions, which is probably why it wasn't great. I don't actually know. Coconut oil probably does have some of those. Fats generally have a thing at the end that kind of mimic how water behaves. So that's probably why it's even stronger. But there are a lot. So we're going to classify these. Let's use this to move into. We're going to classify these forces by what the structure of the molecule looks like. We're going to kind of group them into one of these three categories. And the top one is going to be the weakest one. But all molecules will have that weakest one, which I think is what you're getting at. So everybody's going to have the weakest one. The question is just, do they also have one of these stronger ones? So although everything has the weakest one, we usually care about what is the strongest of the forces that it has. Okay, so three main types of these intermolecular forces. And like I said, you're going to be able to look at the structure by the end of class and identify which of these three types it is. Okay, so the first one, like I said, all molecules and atoms have this. It's just that some only have this. Okay, some molecules will only have these dispersion forces. And specifically, we're talking about nonpolar molecules are the ones that will only have this type. So I'm just going to write that in. So nonpolar will have only dispersion forces. So like it's the only type that they have. Whereas you can see on the next line, polar molecules have this additional type of intermolecular force. That because it's down the column, we know it's stronger. We'll talk about why in a second, but it is a stronger force than that dispersion force. So I don't know why. There's like 5 different names for dispersion forces. I'm pretty sure your textbook is pretty good about just using the term dispersion force. The problem is they might be consistent, but the second you like hear me talk or you look at a video online, you're going to hear all these different names. So let me go ahead and tell you what those are. So van der Waals, this is the guy who coined this or talked about this type of force. So van der Waals force. London forces, no idea where that came from, because Van der Waals, that's obviously Dutch. So I don't know what the connection is to London, but whatever. And then dispersion forces. And then my favorite is called induced dipole forces. And I'll explain why that kind of sets it apart from this next one that's called dipole forces. And it tells us a little bit about how and why they form. Okay, and then there's one additional class that's kind of a subset of dipole forces. This is the one that's annoying. We call them hydrogen bonding. I'm going to put force in there because it's not really a bond. And these are also polar molecules. That's why it's a subset of the one above. But they are a very special type of polar molecule because they have a very polar bond within them. And the way we know this is if it has a hydrogen bonded to a fluorine or an oxygen or a nitrogen somewhere within the molecule, then it will fall into this class of hydrogen bonding. So water's very obvious because it's just oxygen and hydrogen. The one above, the black one's carbon, these are hydrogens, this is oxygen. The oxygen and hydrogen are not bonded to each other, so that's why this would not count as hydrogen bonding. You have to actually, it doesn't matter if they're in the same molecule. This NOF, one of those has to actually be bonded to the hydrogen. Okay, so before we get into the nitty-gritty of explaining why is one of these stronger than another, let's just develop like a little flow chart for ourselves. Let's see, there we go. Okay, so the first thing we're going to want to ask is the molecule polar? So this is going back to chapter 11. You may have to draw the structure. Right? Like you might not immediately be able to identify whether it's polar or not just by looking at the chemical formula, because we know that polarity goes back to the three-dimensional structure and how it's arranged. So simple example, if you have like, not C2, if you have Cl2, F2, okay? If someone looks at that, they might picture this and might think that it's nonpolar because they have the chlorines right across from each other and it looks all nice and symmetrical. But you got to remember that in three-dimensional space, this is tetrahedral. And so those polar bonds, the CCl and the CF, those don't cancel each other out. They're not directly across from each other. They're like this and like this, right? So this case, this one would be polar. So just be careful with that. They're not going to be, I'm not testing you specifically on determining molecules' polarity at this point. So most of them are probably going to be familiar if you were comfortable in chapter 11. You're going to be like, oh yeah, I don't even have to draw that. Like I know what that looks like. Okay? But if there's ever a question, go ahead and draw the Lewis structure. And sometimes I will give you the Lewis structure just so that I'm clear that I'm testing you on intermolecular forces and not just on polarity, because I don't want that to be like a sticking point. Okay? All right. So that's the first question we're going to ask ourselves is it polar? If it's not polar, then the only force that it can have is these dispersion forces. And those are relatively weak compared to the others. So we'll say those are the weakest. Then if it is polar, you got to ask yourself another question. Do you have that nitrogen-hydrogen, oxygen-hydrogen, or fluorine-hydrogen bond within the molecule? So if you don't, that means we're kind of talking about like a simple polar molecule, not one of these special ones. So that would be the dipole force. Which is kind of our mid-strength one. And then if it does have one of these, then that's the hydrogen bonding, which is going to be our strongest. I don't know why I don't have this as a typed part of the notes, but pretty sure every year I think, oh, we should do a flow chart. Okay, so the ones that are the weakest, we're typically going to see those as having low melting points and boiling points. And what this means is that if it boils really low in temperature, it's very possible that at room temperature, it's already boiled. Like it already had enough energy to turn into a gas. So think like carbon dioxide or oxygen gas or nitrogen gas, okay? All of those have, or for that matter, natural gas, methane, okay? Those have all already gotten to their boiling point by the time they get to, 20, 25 degrees Celsius. So another characteristic that we'll see typically, now this is a generalization, usually gas at room temperature. Now, once we get into understanding this stuff a little bit more, of course, I'll give you the exceptions or more detailed ones. But generally, for relatively small molecules, they're going to be gases at room temperature. Okay, the dipole ones, mid-boiling point. This one has probably a pretty big range. So they might be gases, they might be liquids. Depending on their size, they could be even solids. The hydrogen bonding, these are our higher melting points and boiling points. So we'll say liquid or solid at room temp. And I just didn't put anything for the middle one because they're somewhere in the middle. When we compare things between different groups, it's important that we're only changing one thing. So the mass of the molecule has a lot to do with the strength of the intermolecular forces. Once we start talking about within a group, this will become apparent. But something that has a mass of 30 grams per mole is going to behave very differently than something that has a mass of 100 or 200 grams per mole, okay? No matter what their forces are. So when we compare things between groups, we're going to compare things that are relatively similar in mass so that we're only changing the types of forces that they experience, not the size of the molecule. Big molecules tend to have stronger forces and therefore higher melting points and boiling points, no matter what their intermolecular forces are. Again, don't focus on that right now. We'll get to it probably on Friday. Okay. So after we talk about why this is the case, like why the dispersion forces are weaker and why hydrogen bonding is stronger, what we'll do is come to this chart, and we'll use that flow chart to identify what is the main or the strongest intermolecular force that exists in each of these molecules. So that's like where we're headed with this. But first, we need to conceptually understand like why are dispersion forces weaker and why as it gets stronger as you get, a polar molecule, et cetera, et cetera. All right, I want to start with polar molecules because they're the easiest to understand. So this example here, this is carbon, oxygen, hydrogen, okay? So the carbon-oxygen bond is relatively polar. It's about a difference of 1 electronegativity unit. Carbon and hydrogen are pretty non-polar, okay? Even if you want to think of them as polar, they're very small by comparison. So that's like 0.4 versus 1 unit. So that CO bond does not get canceled out by any means by the CH bond. Like if these were both oxygens, it would be trigonoplanar and it would be non-polar. But because they're hydrogens, that's a polar molecule. Hopefully that stuff is still quite fresh since it was just last unit. So when that happens, you create these partial charges, right? The partial negative is on the oxygen, the partial positive is on the carbon because it's less electronegative. And those are what we would say are like permanent dipoles or permanent partial charges. I'm going to use the word dipole more because that's what the book is going to use. When I say dipole, remember I just mean that difference in charge, the partial charge that exists. Permanent dipole. Partial positive, partial negative. And by permanent, I mean it's like inherent in the molecule. So the structure of the molecule is what creates that partial positive and partial negative. There's never a time when it doesn't have that. It's just inherent in the nature of the molecule. In fact, I'll write that. Inherent in molecular structure. Okay, so we've actually talked about this plenty of times before, even like last semester. The idea of something having partial charges, when you get those close together, they start to attract each other in a particular way. So when you get this oxygen here that has a negative charge, the other oxygen is not going to come line up with it because they both have negative charge. That would be a repulsive force. So you get the carbon side of that molecule lining up with this oxygen. Same thing happens with water. Remember, like the hydrogen side gets attracted to the oxygen side of a nearby molecule. That is the intermolecular force. The attraction there between that partial negative charge of one molecule and the partial positive of another, that's your dipole-dipole force in this case. So this is your intermolecular force, in this case, dipole-dipole. So So when we call it that, we're just kind of giving it a grading of like, okay, this is my intermolecular force. It's coming from a permanent dipole that exists as part of the molecule. And so I know that it has kind of a mid-range strength. So I'm going to label it so that everybody knows what type of strength it has. Okay, let's do the hydrogen bonding next. I did it the other way in my other class, but, you know, gotta mix it up a little bit. All right, so water has one of these hydrogen-oxygen bonds. So what's the big difference? Why does water behave so differently if it's just another polar molecule? So if you remember, fluorine is our most electronegative thing. It's got electronegativity of 4.0. Oxygen is 3.5 and nitrogen is 3. And then hydrogen is like 2.1 or 2.2. Okay? So what happens is that you get a very polar bond here that isn't completely the whole story. There is, 2.5 and 3.5. Yeah, that's interesting. It does have to do with the size of these atoms as well, but like these three atoms, along with hydrogen, create a very polar bond, both because of their electronegativity, as well as the fact that they're very small atoms. The size of the atoms allows them to get really close to each other, and that actually increases how polar they are. I don't want you to fixate on the size thing, but if you start to calculate values, you might be like, wait, is it really that polar? It's not just about the electronegativity difference. It has to do with the size of hydrogen and of these other atoms. Remember that corner of the periodic table that's very electronegative, those atoms are also very small, and hydrogen is very small. Okay, so these specific ones create this very polar bond. So when we look at the electronegativity difference here between the oxygen side and the hydrogen side, I'm going to like dramatize this by drawing those partial charges a lot bigger. Okay? So because it's very polar, that's going to create a larger difference in charge. So I'm just making up numbers here, but maybe these guys are like 0.8 negative and 0.8 positive, whereas maybe the ones on the one above is like 0.5 positive and 0.5 negative, okay? It's a partial charge, it's less than 1, but maybe it's a bigger partial charge. Not maybe, it is. I don't know what the number is, but it is a bigger one than would be in the formaldehyde. Okay, so the bigger a partial charge, the stronger the attraction is going to be. If I have two small magnets, it doesn't take a whole lot of energy for me to pull them apart. Whereas if I have two really big magnets, that takes a lot of energy for me to break them apart. The same thing is true here. The larger amount of partial charge it has, the stronger it's going to hold together. Another example, like sodium and chlorine, that's a much stronger bond too. It's a full positive and a full negative. Even stronger than that, magnesium and oxygen, 2 minus and 2 plus. That's an even stronger bond, okay? The bigger the charge is between two things, the stronger that interaction is going to be. So if I've got a 0.8 partial charge between the waters, that's going to be a stronger interaction than a 0.5. Okay? So the more polar something is, the bigger the partial charge is created, and therefore the stronger the interaction between the molecules. Okay, the last one we need to talk about is this weird one with the dispersion forces, because we just said that that is nonpolar. So why in the world do we have partial charges written up there if it's existing in nonpolar molecules? Okay, so here's the thing. Everything has electrons, and nothing is acting completely independent. It's all part of a bigger system, right? Like, you know, think of like you rub your foot on the carpet and you have this buildup of charge, and if you touch someone, you get shocked. My treadmill shocks me like all the time, like enough that I'm like a little startled. So there's a buildup of charge. That's what getting shocked is there's some electrons building up and then it gets transferred to you, okay? Well, let's say we have a buildup of charge somewhere nearby this nonpolar molecule. Now, this one just shows it as an atom. That's because this is the same way we model like noble gases, so argon or neon or something like that. It's just an individual atom. Technically, that would be an interatomic force, not an intermolecular force, but they behave with this dispersion force as well. This could also be like CO2 or nitrogen gas, any of those things, okay? Something nonpolar. So you've got this nonpolar thing that doesn't have an unequal distribution of charge, but then somewhere in the room, there's this little bit of buildup of charge. Okay, well, if I have a negative charge buildup right here, and I have an oxygen molecule here, what do you think the electrons in the oxygen molecule are going to do? They're going to get pushed away from this negative charge. So that's what we're describing here, is it's like, let's start on this side. I've got some buildup of positive or of negative charge here. These electrons kind of scoot over to the side just because they're being propelled by this negative charge. Well, then what happens? There's another molecule nearby. Its electrons scoot away. And this like propagates through any neighboring molecules, and you end up with, reason I like this term, these induced dipoles. So they're very small partial charges. Okay, so I'm going to draw them teeny tiny. I can't even draw them small enough to represent it. Maybe they're like 0.01, okay, positive, and 0.01 negative. They're very small, but they have this unequal distribution of charge, not inherent in the molecule, but it's induced, it's caused by just like this shift in charge that happens naturally because there's never not a distribution of charge in a room or in an environment, okay? So they're not part of the molecule. They just get pushed around and like, what's the word I used in the other class? I can't think, like propagated through, like it kind of like flows through the other molecules. Maybe it'll come to me. So because it's not inherent in the molecule, it's very, very small, but it still creates an attraction between the molecules. But it's really small, so it's easily broken. That's why we see these having relatively low boiling points. That's why carbon dioxide and neon and nitrogen gases are all gases at room temperature. Don't forget, all molecules actually have this going on because they all have electrons. So the electrons can always shift. But it's most obvious in things that are nonpolar because that's the only force that's holding them together. Okay, let's use our flow chart. I'll do like one or two with you, and then I'll have you guys do these on your own. So if you look at these, just kind of scrolling down, hopefully you can see that a lot of these you're going to be able to picture what they look like because you've drawn these Lewis structures before. But just in case, like you can always draw them if you need to. Okay, so there's the first one, CHBr3. Tetrahedral, polar bonds, but not such that they're going to cancel out. So if it is polar, then the next question is, do I have hydrogen bonded to nitrogen, oxygen, or fluorine? No. So it's just dipole, dipole. And don't forget, all of them have dispersion forces because they all have electrons that are moving around. We don't need to necessarily write that on every single one of these. I'll just write it above. All have dispersion. Mainly, I just want you to tell me what's the strongest intermolecular force that they have. Let's look at guanine over here. I think we've talked about this. When we draw organic molecules or like biological molecules, it's annoying because there are so many carbons and hydrogens. So when we draw them like this, every time there's a bend in the molecule, unless there's an atom written there, like it is with nitrogen, it is telling you that it's carbon. So like this would be a carbon, that would be a carbon, this would be a carbon, that would be a carbon, okay? So just for reference so that you can read what the molecule is. So in this case, I've got probably lots of polar bonds there and a very odd structure. They're definitely not canceling out. Also, I have nitrogen bonded to hydrogen quite a few times, okay? Nitrogen, hydrogen, nitrogen, hydrogen, etc. So this is going to be hydrogen bonding. Okay, so use your flow chart and take 3-4 minutes. Basically, we'll do it right up till the end of class. Just give us a minute or two to review them. And I want you to label each of these as whatever its strongest force is. So hydrogen bonding, dipole, dipole, or dispersion. So as you're working, you can go ahead and check your answers. you'll notice that like all of the ones on the right, those are all biological molecules. They're all hydrogen bonding. It's like a very significant property that appears in biological molecules. It's got a lot of functions. I think it's the primary reason why we see DNA in the structure like the double helix, because as it wraps around, parts of the molecule end up getting attracted to the thing that's across from them, and they actually form, I guess you wouldn't call it an intermolecular because it's within the same molecule, but they form an interaction that holds them in that shape. Couple to like notice, this one, even though it has hydrogen and fluorine in it, they're not bonded to each other. So the hydrogen would be bonded to the carbon, and then the fluorines would be bonded to the carbon as well. So like if that's going to trip you up, if you don't notice that, then just draw the Lewis structure. Same thing with this one here. This is the one we saw above where it's got the oxygen bonded to the carbon, and then the hydrogens are bonded to the carbon as well. Whereas in this one, you've got, I'll just draw it. Looks like this. So you've got that oxygen bonded to the hydrogen. Okay, so that's definitely one to keep in mind. All right, I'll leave those up in case you need to finish copying them, and then we'll talk about kind of the effects of this on, or look at effects on melting point and boiling point on Friday.